So non-reacting gas mixtures, most of the topics in this chapter you've already learned in chemistry, hopefully. So why do we need to study this chapter? Well, so far in all the chapters 3, 4, 5, 6, all the way to the current chapters, we took the material to be a pure material, meaning entirely consisted of one chemical formula like R134A, air, other gases like nitrogen, hydrogen, any ideal gas, water, steam. So far it's been just a pure substance, but in engineering situations we deal with mixture of gases. Now we cover non-reacting gases for now, and well, generally in thermodynamics, and we do not cover any chemical reactions. So how do we determine the properties of a mixture of gases instead of a single gas? So let's say you're working on the design of a natural gas pipeline. So we know that natural gas is a mixture of several gases. So what is the density of natural gas at 40 degrees C? One would say just take methane, but that is not accurate because natural gas is not entirely methane. It's a mixture of several gases. What is its specific heat? It becomes a little bit more complicated. And what is its gas constant? Again, taking methane as natural gas is not entirely accurate. So let's look at, for example, the composition of natural gas. You see about 95.2% on a mole basis is methane, but there are other elements in it that will affect the properties. So mass and mole fractions, as I mentioned, you have learned these in chemistry. So the mass of the mixture is equal to the sum of the masses of its components. So we have 6 kilograms of hydrogen, 32 kilograms of oxygen. Mixed together, you'll have 38 kilograms. So mass conservation applies, and mass fraction for each component is just mass of that component divided by total mass. So for hydrogen, it is going to be, you grab a pen. For hydrogen, it's going to be 6 divided by 38.158, and mass fraction, so MF is mass fraction. Mass fraction of oxygen is 32 divided by 38, or by mass, the mixture is 84% oxygen, 16% hydrogen. Mole fraction is based on total number of moles. So if you have 3 kilomoles of hydrogen, 1 kilomole of oxygen, then you have 4 kilomole of a mixture of hydrogen and oxygen, and we use the symbol Y for mole fraction, and for hydrogen it is 3/4, for oxygen it is 1/4, or 25% by mole is oxygen, and 75% is hydrogen. The relation between mass and number of moles, M is equal to N, number of moles, times molar mass. Molar mass of each gas or substance you can find on table A1, the back of the book. So the apparent or average molar mass of the mixture is calculated when you multiply mole fraction of each component. I stands for the component index in a mixture. So multiply the molar mass of that component by mole fraction of that component and then add them all together. You get the molar mass, apparent or average molar mass of the mixture of gases. Doesn't matter how many components are in the gas mixture. And you can easily, using this equation over here, you can find the relation between mole fraction and mass fraction. So mass of each component is the number of mole of that component multiplied by molar mass of that component divided by that for the mixture. So this part is mole fraction of the component I.